Hope you've received the previous recordings and also the lecture notes. So I would like to start off by just giving a brief recap of what we've already discussed. We've talked in the first lecture about notation. We've introduced the concept of Gates. We've looked at quantum states. And we've also talked a little bit about superpositions. In the second lecture, we gave an example of a quantum interferometer. And we saw how the concept of a phase phi leads to some really useful outcomes. Furthermore, we've also looked at the concept of measurement and defined in the process inner products. And we've seen that the quantum computer that we were talking about, the interferometer, starts off with some state preparation, and then you have a sequence of operations. In our case, the sequence of operations was based upon just a minute. I just want to get rid of this Zoom screen uh, from my. All right. So our sequence of operations was a pair of beam splitters, a pair of mirrors, and possibly a phase medium in between. And there was an output state. Say, let's call that output state psi dash. And then we had some kind of measurement. The measurement in our case comprised two detectors placed after the beam splitter. So let me draw this scheme. So after the beam splitter, we have two detectors, P0 and P1. So this is the general idea of a quantum computing experiment. That is, you have some initialization process. Generally, you create a superposition. In our example, the superposition was created by this beam splitter B1, and then you have some quantum process which manipulates the input quantum state. You have a final state, and then you perform a measurement. So in order to do a successful quantum computation, you need an initialization process, you need some quantum transformation, and you need to be able to do a measurement. And you need to do your processes fast enough that you can preserve the superposition. You're always fighting against this superposition going away. The going away of superposition is generally called decoherence. And this is the enemy of quantum computation. Whenever you would like to do a successful quantum computation, you would like to fight against and mitigate the process of decoherence. And decoherence is defined as measurement by the environment. It's an undesired measurement. The environment is interacting with your system of interest, and it continuously collapses the interferences and the superpositions and any entanglement that you have. And we're going to talk about entanglement later in this course. So this is the general scheme of a quantum computation, and this is what we've covered so far. And we're going to build upon this idea today. So at this point, before moving on, I would like to take a couple of questions is so that if any confusions linger on from the first two lectures, I can attempt to answer them. So I'll be happy to take one or two questions here. You can just speak up or write in the chat box, please.
Assalamu alaikum. I have one question regarding
Yes.
initialization. During initialization, is it important to define the base as well? Are we taking the plus base, x bases, or z bases, or y bases, because that might affect the queue processes? So don't we have to, define the bases as well, or the bases are by default z bases? If
No,
I'm
we
talking
have to
about,
define the we have to
okay.
define the basis, and I'm going to start today's discussion with a discussion on basis. We do have to know what basis we're talking about, because the measurement is also performed in a particular basis, so everything has to be consistent, it has to gel together. Yes, bases are really important.
And following that, another question: can a qubit of one base be processed by a Q process of another base?
You see, the basis is a representation. The basis does not affect the physical process. If you would like to make sense of measurement and what the quantum computing is doing, you need to define a basis. But whatever happens does not depend upon the basis. Physics is independent of the basis. So even though you need to know what the basis is to explain what's going on, the basis does not change the outcome. It depends upon the kind of beam splitter you have, what kind of input states you are putting in. That defines the process, not the definition of the basis. The
Okay, thank
computation
you.
is independent of the basis, but you need to
Oh,
know the basis so that you know what you're talking about.
okay, thank you.
So in today's lecture, any more questions? All right. So okay, so let's move on. Today we're going to focus in fact on this thing here, quantum processes. And we're going to describe these quantum processes in terms of quantum logic gates. Now, quantum computing has really evolved over the past 25 years. And the paradigm of quantum computing that is employed today is very different from what I'm going to describe. But the way in which I'm going to describe will help the beginner feel motivated about quantum computing, and it's easier to understand. So bear with me if you find that most of the quantum computers, the Intel, the IBM quantum computers, that there is so much hue and cry about, don't use this model or this paradigm or this way of thinking. But I'm sure that by understanding the fundamentals in a fruitful fashion will help go a long way in your understanding of modern quantum computers. So we're going to use a circuit model to describe quantum computers. And this is how I learned about quantum computers in the first place. All right, so far so good. In order to begin understanding the circuit model of quantum computing and start doing something useful out of quantum computers and building quantum computers, you need to know the concept of, as my friend just talked about, the concept of a basis. Now, if I look at a qubit, I know that the most general form of a qubit is ket psi, which is given by some complex number C naught ket 0 plus C1 ket 1. And C1 and C naught are complex numbers. And these coefficients here, they are also constraints. That is C naught modulus square plus C1 modulus square has to be equal to 1. And this comes out because of normalization. Now, there's something that you might notice here. That is, a general quantum state, psi, has been decomposed as a superposition of ket 0 and ket 1. Now consider a vector. in a two-dimensional space. That is just a piece, a plane of paper or the computer screen, something which is flat. And I draw this vector by an arrow. Let's call this vector A. Now, in order to define A, I need to know its magnitude and I need to know its direction in order to specify its direction. Now, if I write this vector A and I orient it in a certain direction, that's enough to describe the vector. But now if I would like to manipulate it, I would like to represent it, I need to choose some reference axes. The reference axes that I may choose could be a horizontal axis and a vertical axis. Now, this horizontal axis I could label as EX, and I put a small hat on top of it to show it's a unit vector. And the vertical axis I can label as EY. Now, the vector A will have a projection on each of these axes. So I can express the vector A as some projection on axis X, and I define, put along with it the basis vector Ex plus Ay, which is the projection along the y-axis, and I append it with the unit vector itself. Now, in this form of writing a vector, Ex and Ey are basis vectors. We all know this much about vectors. So the same concept really carries over to the quantum state, in which ket 0 and ket 1 are basis kets. And this vector psi can be written as a superposition of basis kets with certain projections. The C0 and C1 are projections, and they are called probability amplitudes. And they're not probabilities themselves, because you need to take the modulus square to find out probabilities, but still they are in dimensional terms proportional to the square root of probabilities. So any quantum state, most quantum states, by the way, which are pure, I haven't described pure or mixed states, but for the sake of simplicity, let's say that all quantum states can be represented in terms of a superposition of basis kets or basis vectors. And there is a certain amount of each basis ket. In this particular case, it's C0 and C1. Now, we also know that vectors can be written as column vectors in linear algebra. So if I were to define ket 0, which is one basis vector, and ket 1, which is another basis vector, by a column vector, I can write this in the following fashion. Now the quantum state psi, this thing here, requires two basis vectors, ket 0 and ket 1. Therefore, here we're talking about a two-dimensional quantum system. The dimensionality of our Hilbert space is 2, and such a system is called a qubit. So our column vectors, which represent the basis states, ket 0 and ket 1, must have two entries, like this. Now it's very convenient. It's really up to our representation what we desire to have these two vectors written in such a fashion that we have a 1 here and a 0 here, and a 0 here and a 1 here. So let me remove the boxes now. Okay, look at this. Our column vector ket 0 is represented in algebraic terms, in terms of linear algebra, by a column vector, which has 1 at the topmost position, and ket 1 is represented by once again a column vector which has a 1 in the bottom position and 0 elsewhere. So my quantum state psi, which is really a superposition of ket 0 and ket 1, how could I represent this as a column vector? Could you just speak up, please? If
C1
this,
and
yeah, both of them will be 1. Both entries will be 1. Oh, sorry, they're not going to be 1, sorry. I'll have a
C0
C naught here and a C1 here.
And
Correct?
C1. Yeah.
yes.
So this column vector is a representation of my quantum state psi. Okay, so far so good. So if I have a column vector or a ket which is given by 1 over under root 3 ket 0 plus 2 over under root 3 ei pi by 6 ket 1, then this column vector could be represented as a column vector with a 1 over under root 3 here and a 2 over under root 3 here and ei pi by 6 appended a phase factor with the bottom entry. So every ket can be represented by a column vector. Okay, so far everything is making perfect sense. Now, if I were to take the inner product of a quantum state with another ket, and this is how I would like to represent this. I know that if I take the modulus square of objects of this kind, I may get probabilities. And we've seen examples of the inner product in our previous lecture. Now, this inner product is really a number. This is a number. The answer is neither a ket nor a bra, but it's a number. But how do you get that number? And I would like to translate the idea of column vectors to finding inner products. And how do I do that? I view this inner product as a composition, as a function between two kets, ket phi and psi, just as we did for the concept of dot product of two vectors. And I view this dot product as having a bra phi together with a ket psi. Now I already know that this psi is represented by a column vector with two entries. Two entries because it's a qubit. Now the bra likewise should have a representation as well. The representation of a bra corresponding to the column vector representation of a ket is simply a row vector with two entries. So a ket has two entries and the bra has two entries. For example, if ket phi were given by C naught and C1, then bra phi would have a row vector in place of the column vector, and these entries will appear in the two positions of the row vector with the added transformation that we would need to take the complex conjugate of each of these scalar numbers. All right. So if I were to find out, now suppose this is my ket phi and my ket psi is given by some a naught and a1. Then let's compute the inner product. Bra phi with ket psi is simply the row vector c naught star c1 star being multiplied by the column vector a naught a1. And the answer is going to be c naught star a naught plus c1 star a1. And of course, this is a pure number. It could be a complex number, but it is neither a column vector nor a row vector. It is a pure number. Okay. If I were to take a column vector or a ket psi and find its inner product with itself, all right? I'm just doing the projection of a vector with itself. Let's see what's going to happen. So my psi suppose is a naught a1. If I pre-multiply it with the row vector a naught star a naught 1 star, I will get a naught star a naught plus a1 star a1. This is a naught modulus square plus a1 modulus square, and this must equal 1 because of normalization. So if a ket satisfies this property as it should, every legitimate quantum state should satisfy this property. We say that the quantum state is then normalized. All right. So this finishes my discussion of representing kets. We need to define a basis. We need to represent that basis as a sequence of zeros and ones. Then we can represent quantum states as column vectors, bras as row vectors, and we can multiply the row vectors with column vectors to get numbers which are proportional to probability amplitudes. So this is the starting point of our discussion on logic gates. So any questions? Am I all clear, or is it not making sense at all? All right. Any questions? Yeah.
It's
All
all
right.
clear.
So let's all right. So let's move on. Now, once we have this representation of quantum states, we need to do transformations on these states. Now let's look at our quantum interferometer once again. I have two beam splitters, non-polarizing beam splitters, two mirrors, and I have a single photon coming in a state ket 0. The first beam splitter produces a superposition, ket 0 plus ket 1, and I divide by under root 2 as well, just for normalization. The mirrors change the path of the single photon. Now, remember, we don't have multiple photons here in this region. Here, we just have a superposition. Okay. And then finally, at the end, we put two detectors. Sorry. You have a detector here and a detector here. P0 and P1. And we perform a measurement right at the end. We don't pry open, be impatient, and intrude into the quantum process. Otherwise, this superposition will collapse and will not be able to see any interference. So this is the general scheme of a simple interferometer. And here, remember that this quantum computer is an example of a single qubit quantum computer. And the degree of freedom that we're talking about is the path of the photon. So just one photon comes into the system. All right. Now, by the way, if you would like to perform this experiment, you cannot talk about probabilities unless you perform the experiment a multiple number of times. So if I were to give you a coin and I would like to ask you whether this coin is fair or balanced, which means whether it has heads on both sides or tails on both sides, or it has a heads on one side and a tails on one side, you toss the coin, you'll get an output. But you can't say if it's fair or balanced by just looking at one outcome. You have to perform the experiment a large number of times. That's why in order to build up probabilities or building up the statistics, you need an ensemble of photons. But still the concept is valid for a single photon. So here we're talking about a single qubit quantum computer. Now, if I were to look at this interferometer again, what I have is are two beam splitters. Now, what each beam splitter does is that it creates a superposition, and we've defined the action of these beam splitters in the following fashion. A beam splitter B transforms ket 0 into ket 0 plus 1, and it transforms ket 1 into a superposition, albeit with a minus sign in between. So this is an example of what I call a gate, a quantum gate. The beam splitter implements a gate. So a quantum device, which is a part of a quantum process, implements some kind of a quantum logic gate. And a quantum logic gate is always defined by a truth table. And the truth table is right here in front of you. This is the truth table for a beam splitter. And it's a special kind of beam splitter. It produces this output given the two inputs. And in order to define the operation of this logic gate, you need to know what is the action of this logic gate on each of the two input states, the two orthogonal input states. All right. So this is what the truth table is all about. You need to know what does it do to ket 0, and you need to know what does it do to the other basis state, ket 1. So so this beam splitter implements a quantum logic gate. Now I would like to write this in linear algebra form, in the form of a matrix or a vector. Now I know that quantum states are represented by column vectors or kets, column vectors. Likewise, quantum operations or gates are represented by matrices. All right. So if I were to represent the action of B through a matrix, and I've already described what my basis states are. Ket 0 is 1 0, ket 1 is 0 1. By looking at the truth table here, this thing here, this thing, look at this. Can you identify what this matrix would going to look like? What is this matrix? Should this matrix be?
One over square root of 2, 0, 0, minus 1 over square root of 2.
What should I write here? Over here, top right?
0.
What should I write here?
0. Minus
here?
1 over root 2.
Let's see if this makes sense. Let's verify this. So this is your candidate B. Now if I have this B and it acts on ket 1 0, which is 1 0, let me see what the output is going to be. It's going to be 1 over under root 2. So is this the correct output? What should my output be? No, it's not. My output should be, let me write down the output. This output state is 1 over under root 2, 1 over under root 2. This output state is 1 over under root 2 minus 1 over under root 2. So what should my matrix for the beam splitter look like? Any more ideas?
Sir, we should write 1 over under root 2 instead of 0.
So 1 over under root 2 here. What should be here at the top right?
1 over under root 2.
And bottom left?
1 over under root 2.
Bottom right?
Minus 1 over under root 2.
So this is the matrix for the beam splitter. Okay. If you notice that the first column, the matrix is a 2 by 2 matrix, because it acts on a vector which is 2 rows and 1 columns to give me another vector which is 2 rows and 1 column. So the all the elements that you use, the matrices and the vectors, should be compatible for multiplication. If I were to take this matrix and act it on any input state, it could be cat 0, it could be cat 1, it could be a superposition, then this matrix defines what the output is going to be. And it works for cat 0 and cat 1, so it should work for any superposition. And you will notice that the first column is really the what you get when B acts on cat 0, and the second column is what the output is when B acts on cat 1. Okay, so this is an easy way, a mnemonic, an easy way to remember how to construct this matrix. And by the way, in quantum computing, these matrices represent quantum gates. You can put a symbol for a quantum gate. Just like you use symbols in normal logic, digital logic, you have a NOT gate, you have a buffer with a certain input and an output, you have an AND gate, which of course takes in 2 inputs and 1 output. You can also have an exclusive OR gate, which has 2 inputs and 1 output, and so on. So these are quantum gates that we're now talking about. And this matrix here is a special kind of matrix. It is customary in quantum computing to represent gates by the symbol U. And this U comes from the word unitary. And I'll explain what unitary means. So this unitary gate of this kind is a special gate which is called a Hadamard gate. The Hadamard gate is was is a special kind of matrix, and the property of a Hadamard matrix is the following. If I took the first column and the second column and find the inner product of these 2 columns, so let's do that. I take the first column. In order to find the inner product, I convert the column into a row vector, and I take the second column and I multiply them out. The answer is 0. Okay. Likewise, if I took the first row and find the inner product of the first row with the second row, I will still get 0. So all the rows are mutually orthogonal and all the vectors in a Hadamard matrix are mutually orthogonal. And this is how a Hadamard matrix is defined. And that is why this gate is called a Hadamard gate. And I can represent this Hadamard gate just by a box, the symbol H or UH inside. Okay. Now, any questions? Now let me ask you a question here. If I had a Hadamard gate, now I forget about the beam splitter, because the beam splitter was a particular technology. It was a particular physical implementation of a quantum computer. Now I can just use the generic language of gates and input states and output states. Suppose I had a Hadamard gate and inputted the state psi, which is, suppose, 1 over under root 2, 0, plus 1 over under root 2 get 1. What should my output be? So when I define logic gates, these logic gates can take any input, any input you provide with them. And you just take the matrix of the logic gate and find out what the output is going to be. So what's going to be the output here? I can do a matrix multiplication, right? So I could take the input state, which is 1 over under root 2, 1 over under root 2 in the form of a column vector, and take the matrix for the Hadamard gate, which is 1 over under root 2, 1 over under root 2, 1 over under root 2, minus 1 over under root 2, okay? And I just multiply things out. I get, multiply this with this and this with this, half plus half is 1. Multiply, then I multiply this with this and this with this, 1 minus 1 is 0. So my output is going to be cat 0. And we've already noticed this when we were discussing the interferometer yesterday. So these matrix representations of logic gates simplify our lives. Now, what I could also do, I could take the concept of the circuit model a bit further, and I can recast my interferometer to beam splitters B1, B2, two mirrors, and an incoming photon. A superposition is being created. The final beam splitter is interfering the two paths. It's interfering the two possibilities. It's creating interference between possibility 1 and possibility 2. You don't look into the possibilities before the beam splitter, rather you put measurement devices at the rear end of this experiment. Now, this is a physical model. It uses real beam splitters and photons. If I would like to draw a circuit model for the same experiment, I have one qubit coming in. I have a Hadamard gate, H, and this is followed by another Hadamard gate. Since the beam splitters B1 and B2 are just the same quantum device, there's nothing different about the two, they're identical. So I just juxtapose and put two Hadamard gates together. So what I've drawn on the right is a circuit model description of a quantum interferometer. Okay? And this will explain all the outcomes that I can think of. So what we did in the previous lecture, I input cat 0. This gate creates a superposition. This gate, the second beam splitter, does an interference, and the output is again cat 0. And if I were to place or insert a medium here, and that is a phase medium, and what the phase medium does, you need to, of course, for any operation, you need to define a logic gate and you need to define a truth table. The truth table is basically you take the two inputs, the two basis inputs, and determine or tell us or tell the experimenter or the implementer what that particular process should do. And we've defined the phase gate to do the following. It does nothing to cat 0, and it adds a phase phi to cat 1. Now, if I were to write a matrix, let's call that matrix U phi. Can anyone just tell me what that matrix is going to look like?
Yes.
Yes, please.
1, 0,
Mm-hmm.
0,
Mm-hmm.
e to I phi.
E to I phi. Exactly. This is what the phase gate does. So this particular experiment can be described by a circuit model in which there is a Hadamard gate and another gate. Let's denote that gate by a simple dot, put a phi on top of it to show that it's a phase gate, followed by another Hadamard gate. Okay. Now, by the way, this quantum computer that I've drawn here, this is a possible quantum computer. You can feed it with any input state. It will give you some output. Now, the cleverness of the algorithmist, or one who defines quantum algorithms, is to choose what input states to use and how are measurements being performed. But nevertheless, you can input it with any quantum state. Suppose my input state was a really general state, C naught, C1. I can, of course, use all the all the things that I've learned so far. Now, this is a sequence of three operations: a Hadamard gate followed by a phase gate followed by another phase gate. What I could do, let's call this input state psi, and let's call my output state chi. Now, how do I determine chi? Chi is determined by, I have the input state psi. The first matrix that acts on this input state is the Hadamard matrix, UH. So this will be the state that is going to be created at this point here, okay? At this interim position, but you don't look at it. Then you have the phase gate, U phi, acting on the state that is produced at A. When you've applied this gate, you are at position B, this position B. And then you append the transformation with another Hadamard gate. So this is going to be your final output. And you could take C naught C1 in place of psi. For the Hadamard gate, you could write this. For the phase gate, you could write this. For this Hadamard gate, you could write this. And this will be your output state chi in column vector form, and you can always write this as a superposition of ket 0 and 1. Okay, so notice that even though in the diagram it's conventional to take the initial states on the left and the output on the right, when you write this in matrix form, the time ordering is from right to left. So this is the direction of time. I think I need to change my battery. So I can take one or two questions in the meantime while I change the battery.
I have a question, please.
Yes, please.
What about mirrors in circuit models or circuit representation?
Now, who asked this question?
Sajida.
Right. So the mirrors have no role as far as the quantum computing is concerned, because the role of the mirror is simply to change the direction of the optical beam, and it's just for our understanding. So sometimes you would like to add a phase shift. So when a reflection occurs, a phase shift occurs, but it occurs on both ket 0 and ket 1, so it doesn't really matter. So for our purposes, the mirrors are doing nothing quantum mechanically. They are just shifting the position of the beam. They are steering the beam, in other words. Okay?
Okay, thank you.
Right, for some reason any more questions?
There's one more question, sir.
Yes, sir. I got one. So,
Yes.
So if the mirrors do not change the phase, sorry, it does change the phase, but it doesn't do anything quantum mechanically, and it just changes the phase. How come in the beam splitter example, in the interferometer that you discussed, How come, the phase does change in the two directions, right? In the horizontal and the vertical. And for that case, as far as I understand, that isn't those the basis for that system, the horizontal and the vertical directions, and that has a phase, quantum mechanical phase change, if I understand it right.
So if I were to put a phase medium in between, that is adding a phase. That is a phase gate, right? There's no doubt about it. But the mirrors, in my example, they don't add a phase. In some examples, the mirrors do add a phase. You can have dichroic mirrors or certain kinds of mirrors which add a phase to a particular uh, to a particular polarization state, or to a particular path, but that's not of my concern at the moment.
I have a question.
Yes, please.
So is the Hadamard gate defined by being its two columns being their inner product being 0, or is the Hadamard gate exactly just the matrix that we found, 1, 1, 1 minus 1?
The Hadamard matrices were proposed by Hadamard well before quantum computing, or well before any quantum mechanics. A Hadamard matrix is a concept in which has a property. Number one, it is itself adjoint, which means you take the Hadamard and its adjoint, it's the matrix itself. You put two Hadamard matrices, multiply them with one another, you get the identity matrix, and that is possible when each row, all the rows of a matrix, they are mutually orthogonal. So if you have a 4 by 4 matrix and you take any two rows and find the inner product, it's going to be 0. And the same applies to all columns. So it's not only this matrix. You can have 4 by 4 matrices, 8 by 8 matrices, and all of them qualify as Hadamard matrices if they satisfy these properties. Okay?
Thank you.
I have a question.
Yes.
Do Hadamard matrices differ from Hermitian matrices?
Yes. A Hermitian matrix is a matrix whose adjoint is the matrix itself. But it's not necessary that so if I take a matrix, sorry, my this thing has stopped working. I cannot write at the moment. But if I were to take a matrix, say 1 0 0 0, which is just one entry, which is 1, then this is a Hermitian matrix. But it's not a Hadamard matrix. If I take the 1 half, 1 half, 1 half, 1 half, this is a Hermitian matrix, but it's not a Hadamard matrix. Okay?
Thank you.
And sir, I read something about the Hadamard representation, the basis representation. So how does that fit into this picture of the Hadamard matrix? Does it have anything to do with the basis, the Hadamard basis representation as well, or is it something completely independent of that?
No, they are related, Mustafa. They are related. The Hadamard representation is a representation in which you use Hadamard matrices as the basis. So slightly complicated, but they're related. It's the same concept here. What I've done here is I've defined a Hadamard gate. And the Hadamard gate, as you can see from my screen has stopped working, sorry about that. As you can see, is just a matrix that creates a superposition or collapses a superposition. So if you give me 2 or 3 minutes, I would just like to restart my computer. Just give me 2 minutes, please, and I'll
Sure,
just
sir,
be
sure.
back.
Okay.
All right, I'm going to share my screen again. Can you hear me?
Yes.
All right, okay. Thank you. Sorry for this slight glitch. So we've talked about quantum gates. If I were to write a 4 by 4 matrix, sorry, for some reason it stopped working. All right. So if I were to write this matrix, just I'm putting 1 over under 2 outside the matrix. 1, 1, 1, 1. Okay. Now one can see if whether this is a Hadamard matrix or not. So one can write different kinds of matrices and investigate whether they are Hadamard or not. So we can have a 4 by 4 matrix, we can have uh, a 2 by 2 matrix, and so on. I'm just turning off my video for a minute because I don't have much time to set it up right now. So we can have different kinds of quantum gates. So let me give you another example of a gate. Suppose I define a quantum gate and I call it a quantum Naught gate. Okay. By the way, the example of a Hadamard of the beam splitter is really important. So if I have the following, so if I had a Hadamard gate followed by a phase gate which has a phase pi, followed by another Hadamard gate. Okay, so instead of having an arbitrary phase gate, I would like to have uh, a phase gate with a particular value of phase. Now, could you tell me if the input for this gate were ket 0, what would the output look like? What should be the output?
It should be the same, right?
Same as so if my phase were 0, if I didn't have a phase gate, what would be my output?
0.
0. So if my phase were pi instead of 0,
1.
get 1, right? So I can test this out as well. So my initial state is ket 1, 0. My first Hadamard gate is, I'm putting 1 over under root 2 outside. This is 1, 1, 1, minus 1. My phase gate is 1, 0, 0, e raised per I pi, which is minus 1. And then I have another Hadamard gate at the output, 1, 1, 1, minus 1. So let's see what my output is going to be here, chi. Okay. So this is 1 half, 1, 1, 1, minus 1, 1, 0, 0, minus 1. I will get 1 here and I will get 1 here. Okay. Then I get to the next step, 1, 1, 1, minus 1. And then I implement the phase gates. What do I get? 1 here and I get a minus 1 here. And then let's see what happens. 1 minus 1, 0, and I get 1 plus 1. So my output is ket 1. So just having two Hadamard gates and intervening in the two Hadamard gates, there is a phase gate. Something really interesting happens. I always invert the input. And if I were to input a ket 1 gate, I would get a ket 0 at the output. So two Hadamard gates are inverting the output provided in between there is a pi gate. Now, this is really interesting. If I were to compose this pi gate, So let me conceptually at least think of the following. I have a Hadamard gate and I have a pi by 2 gate, followed by another pi by 2 gate and a Hadamard gate. Now you can imagine that what I drew above was a single phase gate. Now what I've done here is I've cleverly split the phase gate into two pi by 2 phase gates. And those two pi by 2 phase gates, one after the other, they have the same impact as a pi gate. Now this concatenation of a Hadamard gate with a phase gate followed by itself, though in the reverse order, qualifies as a square root of a Naught quantum gate. And this is also a square root of a Naught quantum gate. Because when I put the two gates together, I get a Naught operation. And it is only quantum mechanically possible. And with the strange impact of phasors and interferences and phases that you can have gates of this kind. Now, quantum Naught gate, if I were to write the matrix for a quantum Naught gate, so I want to write the unitary matrix for a quantum Naught gate. Can anyone tell me what the matrix is going to look like?
Sir, 0, 1, 1,
Okay,
0.
so what is 0?
0, 1,
0, 1?
minus 1.
No. What should I put at the bottom left?
1,
1.
Mm.
Bottom right?
0.
0.
Okay. So the truth table of a quantum Naught gate is that it takes ket 0 and converts it to ket 1. And it takes ket 1 and converts it to ket 0. Okay. So far, so this is going really good. And all quantum computers must have these single qubit operations or gates. They must implement single qubit gates at least. It's necessary but not sufficient. They need to have 2-qubit quantum gates as well. We're going to talk about them. But single qubit gates is an absolute necessity. And why are these gates called unitary operations? They're called unitary operations for a special reason, is that if I were to take a quantum state psi and a unitary gate acts on it and produces a state ket phi, then a unitary operation is defined as an operation that preserves the norm. What does that mean? It means that if the inner product of psi with itself is 1, then a unitary gate is such that the inner product of phi with itself is also 1. Okay, so it preserves the length of the quantum state. It preserves the gate, the norm, and this is what a unitary operation really means. So if I were to portray this on the block sphere, okay, so this is the last really interesting point. And in the meantime, let me try to restart my camera. Uh, I need to restart this. Okay, it has failed for the time being, but
Sir, there is a question. May I?
Yes.
So there's a question by Iram Mubarak. She says that so there's a slight confusion. Well, if Hadamard matrix is a unitary matrix, then why the eigenvalues are not complex? Because unitary matrices have complex eigenvalue with modulus 1. Maybe I'm missing something here. Second, are all Hadamard matrices unitary matrices?
Yeah, the Hadamard matrix is a unitary matrix. A unitary matrix does not necessarily have real eigenvalues. A Hermitian matrix has real eigenvalues, but a unitary matrix need not have real eigenvalues. Okay. Uh, Mosina, can you hear me?
Yes, sir, we can.
Okay. So now coming back to the unitary
There's one
operations.
more question, may I? Yeah.
Yes, please.
Okay, so it's by Madiha Khalid. She says that what are the necessary unitary gates for the smallest quantum computer?
That's a very good question. For the smallest quantum computer to be of any use, you need to have single qubit operations, which I'm going to talk about right now, and I've given you certain examples of it. And you need to have at least one kind of two qubit gate. And the most common kind of quantum qubit gate that is considered to be necessary and sufficient is a controlled NOT gate. So you need to have single qubit gates of all kinds, and you need to have a control NOT gate. This forms a universal set of gates for two qubit quantum computation. If you were to deal with three qubits, you need a what is called a Fredkin gate or a controlled Toffoli gate. Okay. So for doing anything useful, you need all single qubit gates, and all single qubit gates are equivalent to one another, as I'm just going to explain. And you need at least one two qubit quantum gate, because if you just deal with single qubits, you can explain everything classically as well. But that's not the case when you enter the realm of two qubits. Okay. All right. So I'm going to talk about unitary gates in the last 5 minutes. So we already have seen the concept of the Bloch sphere. In the Bloch sphere, I have a quantum state psi, and that state lives on the surface of the sphere, the Bloch sphere. Now let's take the example of a quantum NOT gate. What a quantum NOT gate does is that it takes a state which is on ket 0, this state, and transforms it to the opposite side of the Bloch sphere, right? It takes it to ket 1. Now, can anyone tell me what does the NOT gate do to a to a to the input state ket 1? If my input state were ket 1 and I applied a NOT gate to it, what
Cat
would
0.
happen? Ket
Reverse
0.
at 0.
So if my input state were, instead of ket 0 and ket 1, if it were something else, so if my input state were here, right, which I'm drawing in purple, which is the state ket 0 minus iota ket 1 over under root 2. And if I were to implement a NOT gate, what would the output be?
0 plus iota over under root 2.
0 plus iota. Let's see. So ket 0 goes to ket 1, minus iota is just unchanged, ket 1 goes to 0. So I can rewrite this as minus iota ket 0 plus ket 1 over under root 2. Now can I take minus 1 common? Now this is my output state, right? This is the output state. Where does this state lie on the Bloch sphere?
On the positive x-axis.
On the positive x-axis, which is, where is the positive axis? Is it here, here, or here?
No. Yeah.
Here? Yeah, we call it the y-axis, by the way.
Yeah. Yeah.
So how do I know that? So I take minus iota common from this output. I write ket 0. What do I need to write here? Plus iota, right? Because plus iota multiplied with minus iota gives me plus 1, which is this state over here. And what do I do with this minus iota? Because the state that I'm actually getting is all of this. Whereas in the previous lecture, I mentioned that this is the state that lives here on the east point. But when I do the calculation, I get this minus iota. Is it of any consequence? So in other words, is the state that I've written in the green wavy box the same as the state that I've written over here? Are these states the same? Or is there any difference?
Same.
They are the same. Because this minus iota is merely e raised to power minus I pi by 2. It's a global phase. And global phases don't matter. Why do global phases don't matter? Because suppose this state is represented as chi. If I were to take chi and overlap it with 0, what would I get? I would get e minus I pi by 2 over under root 2. Okay. Now if I were to take the modulus square of this state, I would get 1 half e plus I pi by 2 e minus I pi by 2. And this phase factor, which is a global phase, just disappears and I get 1 half. So it doesn't matter whether I keep this global phase or not. Its overlap with any other state and you take the modulus square of it, which is corresponds to physical probabilities, doesn't change. That's why the global phase is immaterial. Okay. So now turning back to the concept of this NOT gate, what the NOT gate does simply, as you may recall by now, as you may have understood by now, it takes a quantum state anywhere on the Bloch sphere and simply transforms it to a point on the diametrically opposite side. Is that correct?
Correct.
So geometrically, what kind of operation is this? Is it a kind
Mirror,
of translation or is it a kind of shearing operation? What is happening to the quantum state here?
reflection,
Reflection?
Not a,
Is it really
not a,
reflection? Okay. So who said reflection?
It's invergent through the origin, no?
All right. So okay. So this is really interesting here. So you see, you mentioned it's reflection or inversion through the origin. Okay. So let me draw the Bloch sphere again. Suppose my input state is here. My input state is ket 0 plus 1 over under root 2. When the NOT gate acts on this state, U naught, what is my output?
Same.
It's the same because ket 0 goes to ket 1, ket 1 goes to ket 0, which is just it's just the same superposition, doesn't matter. So this particular kind of state, which is an eigenstate of the unitary operation, is unchanged. It is preserved under the NOT operation. So you can't say that it's always the reflection or it's always inversion around the center. It's something more to it. Can anyone guess what this unitary operation corresponds to in terms of when you look at it on the Bloch sphere? I give you half a minute to think about it, please.
Is it the conjugate?
Conjugate?
Conjugate.
No. So is it a translation? Is it a reflection about some mirror plane? Geometrically, what does it correspond to? And I want to bring home the idea of a unitary operation. Students who have learned about,
replication.
sorry,
Replication.
replication. So here the input state is not being replicated. If this were my input state, I apply a NOT gate to it, Nothing happens to the state. Any idea? Exactly. So Eman Noman says
Rotation.
it's a rotation. Exactly, it is a rotation. Now, when you talk about a rotation, any unitary operation is in fact a rotation on a Bloch sphere. So it's a rotation on a Bloch sphere. When you talk about a rotation, you need to define two things. The first thing is axis of rotation. And the second thing you need to define is the amount of rotation. So now so if I take the quantum Naught gate again, I need to define an axis of rotation. Can you predict, can you predict what would be the axis of rotation for a for a Naught gate? So something that takes ket 0 to ket 1 but does not change ket 0 plus 1 over under root 2.
And
It
then
takes
it's around.
it takes just excuse me for a minute please. It takes this state ket 0 plus iota 1 over under root 2 to here, right? But it doesn't do anything to the ket 0 plus 1 over under root 2 state or the ket x state. So what kind of rotation is it? What is the axis of rotation?
X-axis.
The axis. Yeah, the x-axis.
Exactly. Exactly. So it's a rotation about the x-axis. So this becomes my axis of rotation. Okay. And how much is the rotation? How
Pi.
big is the rotation? Pi. Exactly. So a NOT gate is a rotation about the x-axis or the 0 plus 1 over under root 2 axis, which is generally called the ket x-axis of the Bloch sphere, by pi. And this definition holds. So if I were to take an axis, this axis, and I would like to rotate the red state ket 0 plus 1 over under root plus iota ket 1 over under root 2, I will go here. I can, with the same rotation, take ket 0 to ket 1. I can take ket 1 to ket 0 and so on. But the anything that is parallel to the axis of rotation doesn't change. And that is the property of a rotation operator or a unitary operator. Every unitary operator is simply a rotation operator. It rotates about a certain axis. And these single qubit gates are all rotation operators about the Bloch sphere. Nothing else, nothing more. And these are essential for quantum computing operations. Every physical implementation needs to implement a single qubit gate, which is a rotation operator. It needs to rotate quantum states. It needs more, of course. It needs two qubit gates, but it also needs, it always needs a single qubit operation. Now, I would like to finish off this class by leaving you with one question. We run over time, and that question I would like you to think over before we meet for the next class is: you've considered a Hadamard gate. The Hadamard gate is also a unitary operation. Therefore, it must be described by an axis of rotation and an amount of rotation. So I would like to start off by the next class by asking you to just look at the truth table of the Hadamard gate and explain to me what kind of rotation is it on the Bloch sphere. Thank you very much.
Sir, we cannot hear you.
All right, can you hear me now?
Yes, we can.
Okay,
Your
any
video
question?
has.
All right, so the video I've shut down because there's problems here. So any questions?
Could you repeat the question which you have for the candidates?
Okay, so the question that I would like to ask is, looking at the Hadamard gate, can you explain to me what kind of rotation is it? Hello, can you hear me?
Yes, we can. So if there are any other questions, please unmute and speak up or write them in the chat box. Otherwise, we're going to end the class.
So we should know what the axis of rotation and what the amount of rotation of the Hadamard Gate. Yes, right?
Yeah, I just want to start the next question, next lecture tomorrow, but with the answer to the question is, if I look at the Hadamard gate, what kind of rotation is it? What's the axis of rotation and what's the amount of rotation?
Yes.
Okay, all
Thank
right.
you.
So I think that's enough for today. Inshallah, we'll meet tomorrow. Yeah, it can be called an X rotation gate, Hamza. No problem about that. No problem about that. And by the way, the NOT gate, since it's a rotation about the x-axis, I can always write this as e raised to minus I pi sigma x over 2. So people who know about Pauli matrices can identify that this is what the unitary gate for a NOT operation looks like. But if you don't understand this, that's fine. We'll inshallah continue with our fourth lecture tomorrow. Inshallah. Thank you very much.
Thank you, Professor.
Hello. Mohsina, I think I'm going to sign off now.
Okay, sir.
Okay, okay. Thank you very much. Thank you very much. Ma salam and Allah Hafiz, everyone.